12 slip systems is a lot relative to other types of unit cells. Just take a look at this bad boy, the hexagonal close-packed HCP unit cell, which is found in metals like titanium. An HCP unit cell has a far more complicated atomic arrangement due to its hexagonal geometry and specific stacking sequence compared to FCC. A unit cell of titanium, which is HCP, has 3 basal slip systems. There is only one slip plane that can move in 3 directions. Titanium is therefore far more limited in its capacity to deform compared to gold. Gold has 12 slip systems, so that's why it's more ductile. Now, I've probably given the impression that crystal lattices are these really intricate, perfect structures. I mean, I probably have. Just hearing the word crystal evokes images of gemstones and perfection, but in reality, things are rarely perfect. Crystal lattices are no exception. They're rife with imperfections, and these defects, these imperfections, significantly influence the properties of materials. Defects in crystal lattices can be broadly categorized into different classes based on their dimensional characteristics. Point defects and line defects are the 2 main classes of defects that you should be familiar with. Let's start with point defects. They're imperfections that occur at or around a single site in the lattice. There can be vacancies, so an atom can be missing from its lattice site, leaving an empty slot. There are interstitial defects that occur when an extra atom occupies an irregular space in the crystal lattice. Here we can see a self-interstitial, i.e. an extra atom of the same type as the host lattice, fitting into the spaces between the regular lattice positions. And here we can see foreign interstitials. This is an atom of a different type than the host lattice. These interstitial defects can cause significant distortions in the lattice due to the size mismatch and can affect the material's mechanical properties. And here we can see yet another type of point defect, a substitutional defect. This occurs when an atom in the lattice is replaced by a different type of atom. Now, this can be done intentionally to create metal alloys, enabling you to imbue it with different properties that are to your liking. Alright, so that's point defects. Line defects, also known as dislocations, are, as the name suggests, a defect that involves an entire line of atoms. And they come in different flavors too, just like point defects. The 2 most important types of line defects are edge dislocations and screw dislocations. Now, here's an animation that shows what an edge dislocation looks like within a crystal lattice. The line defect is this extra half plane of atoms. Now, if we visualize the bonds between the atoms and apply a stress to the material, bonds break and reform, allowing the edge dislocation to glide through the lattice. Okay, so let me repeat that. When an external stress is applied to the crystal lattice, shear forces act to move atoms along the slip plane, causing plastic deformation. Atoms adjacent to the dislocation line move to accommodate the motion of the dislocation. This movement involves the atoms on either side of the dislocation line shifting positions relative to each other. So, as the extra half plane of atom glides, the dislocation line advances through the crystal lattice. So this process allows the material to undergo plastic deformation while maintaining its overall crystalline structure. Okay, it's time for a quick recap. So, thus far, we've broadly discussed metals, we've delved into their structure at the atomic level. The unit cells are the building blocks of crystal lattices, which is inherently imperfect, containing point and line defects. That's all well and good. Now, have a good hard look at this sheet of copper. Don't mind the safety pin, it's just there for a sense of scale. Now, the slab of copper has been etched with an acid, and the surface has this irregular pattern to it. So if I zoom in, you can get a closer look at these irregular shapes. But what are they? Given the context of what we now know about metals, can you explain what those shapes are? Right, so to answer that question, let's quickly revisit a lattice made from FCC unit cells. In this image, we can see a single crystal lattice of salt. It's a monocrystal, and we use monocrystals all the time in dentistry. Diamonds coat the surfaces of our burrs. Diamonds are monocrystals made of carbon. Now, as a side note, why do we place great monetary value on diamonds? Well, they're rare, obviously, at least if they're naturally occurring. Scarcity is part of it. I mean, would you propose with a synthetic diamond? Well, it depends if you want them to say yes, I guess. But diamonds are actually graded according to the 4 C's, and clarity is one of those 4 C's. And it's correlated with the presence of imperfections and impurities in the crystal lattice. So if there are internal inclusions or external blemishes on the diamond, its value decreases. A flawless diamond, on the other hand, can be priceless.
It's overwhelming.
This piece of copper is clearly not a monocrystal. It's cluttered with crystals. Copper has a polycrystalline structure. So each one of those shapes is a crystal lattice made of FCC unit cells. In a polycrystalline metal, the crystals are distributed randomly throughout the material, with each crystal having a distinct spatial orientation in relation to its neighbouring crystals. When copper is heated, thermal energy increases the kinetic energy of its atoms, causing them to vibrate more vigorously. As the temperature rises beyond 1000 degrees Celsius, the metal bonds holding the copper atoms in a solid lattice structure break, leading to a phase transition from solid to liquid. So the copper essentially melts, and in this liquid molten phase, the copper atoms are no longer confined to fixed positions and can move freely at ridiculously high speeds. As the temperature decreases, the kinetic energy of the copper atoms decreases as well, causing them to move more slowly and eventually come together in an organized manner. Initially, small clusters of atoms form, which then grow into larger structures as more atoms join them. These structures eventually develop into distinct grains with well-defined boundaries. Each grain in the solidified copper represents a single crystal lattice. And the overall process of solidification results in the formation of a polycrystalline structure, where multiple grains with different orientations are distributed throughout the material. This microstructure influences the mechanical and physical properties of the solidified copper. How, you say? Well, grain boundaries play a crucial role, acting as barriers to the movements of defects like dislocations. In the presence of an applied stress, edge dislocations, for example, will move through the material, allowing for plastic deformation. However, when dislocations encounter grain boundaries, their movement is impeded, much like a brick wall obstructing the flow of traffic. This hindrance limits the ability of dislocations to propagate through the material, thereby reducing its ductility. A metal with smaller grains contains a higher density of grain boundaries per unit volume, effectively increasing the number of obstacles encountered by dislocations. So, metals with smaller grains exhibit decreased ductility compared to those with larger grains. While smaller grains can enhance strength by impeding dislocation movement, they can also introduce a potential weakness, increase susceptibility to brittle fracture. In materials with small grain sizes, the high density of grain boundaries, which are regions of structural discontinuity, can serve as preferential sites for crack initiation and propagation. This phenomenon is particularly pronounced in materials with fine grain sizes, where grain boundaries are closely spaced. As you can see, the crack can easily find a path through the closely spaced grain boundaries. So, influencing a metal's grain size has serious implications. The primary mechanism to control grain size is the cooling rate. When a material is cooled rapidly, a large number of nuclei form, and these nuclei act as sites for the initiation of grain growth. But because the cooling rate is rapid, there is less time for these nuclei to grow into larger grains before the metal solidifies. Conversely, when a material is cooled slowly, there is ample time for nucleation events to occur throughout the volume of the material. So as a result, a smaller number of nuclei form, but they have more time to grow into larger grains before neighbouring nuclei impede their growth. So this leads to the formation of fewer, larger grains with a more uniform size distribution. Now here's a great example of this in action. You must have seen a movie where a blacksmith is making a sword, right? Probably in like some fantasy movie. Once the sword has been forged, there's always that scene where they strengthen it. They heat the sword until it turns red, and metals share electrons because of communism, remember? That's why they turn red. Duh. And to ensure that those grains remain small, the sword is quenched. It's cooled rapidly. Smaller grains make the sword harder and improves tensile strength. Right, so there's one last topic I can squeeze into this lecture. Thermal expansion. A metal will increase in size if you raise the temperature. Now, to help explain how this works, I thought I'd use a graph that can be found in most textbooks about material science. Now, it depicts the relationship between interatomic force and distance for a pair of atoms. The blue curve is the attractive force, and the red curve is the repulsive force pushing the two atoms away from each other. The resultant force curve, which is green, represents the net force experienced by the atoms as a function of atomic distance. So let's see how this actually works. Here are two atoms that have a large interatomic distance separating them, but there is an attractive force that wants to pull them together, and the force gets stronger and stronger as they move closer to one another. So at this point here, we've reached the maximum attractive force between the two atoms. Now if they move closer still, the attractive force will actually decrease as it succumbs to the repulsive force counteracting it. Now at this point in the resultant force curve, the attractive and repulsive forces cancel each other out. So it's the point of equilibrium. This is therefore the most stable position for the two atoms. So this is where atomic bonds are more likely to form, because again, this is where the atoms are most stable. But if we were to continue to push these two atoms closer together, the repulsive force will increase and try to push the atoms back into their previous state of equilibrium. Now remember, if you increase the temperature, you supply thermal energy to a material which is converted into kinetic energy. As a result, the atoms of the material vibrate more vigorously. So imagine these two atoms vibrating with more and more intensity as you crank up the heat. The space, the interatomic distance, increases between the atoms. Now apply this concept to a block of metal and it will expand. So here's another way of thinking about it. You have a group of people tightly packed into a room and they're dancing slowly. They're pressed up against each other, and then suddenly the DJ puts on another track. Everyone goes wild and starts dancing like crazy. They spread out more and they fill out more of the room. It's another way of thinking about it. The coefficient of thermal expansion describes how the size of an object changes with a change in temperature. It's an important concept, and if you fail to understand it, bad things happen. A lovely hot day warms up the train tracks and they warp in the heat of the sun. Apparently, metals thermally expand. Who the hell knew, said the builders of this train track. Adding these nifty little expansion joints to the train track allows the metal to expand on a scorching hot day. In dentistry, understanding the coefficient of thermal expansion is important too, especially when making porcelain fused to metal crowns. Porcelain and metal have different coefficients of thermal expansion, so it's important for them to be similar with an ever so slight mismatch in the CTE because they can actually help bond the two materials together. Typically, the metal substructure is chosen to have a slightly higher CTE than the porcelain. So when the crown cools after being fired, the metal contracts slightly more than the porcelain, and this creates a compressive stress on the porcelain, which helps to hold the porcelain in place and reduce the risk of cracking and debonding. Right, so that brings us to the end of the lecture. So thanks for visiting Isle Ivory. I hope the video has helped you become better acquainted with metals and some of the basics of materials science. Understanding how things work, why materials behave in the way they do, is really satisfying to learn about. How else would you expect to see the matrix if you don't delve into the nitty-gritty of the physical world around you? So with that said, I'm Dr. Jamie. Hope to see you again here soon at Isle Ivory. Take care.